Okay, let's do problem 5 here. This is Saturday morning for me. I just woke up. As one of my students says, I might have that just got out of bed voice going on. So I hope I hope you can hear me and hope I'm coherent and I don't say stupid things. But if I do, please pardon me. So basically, this question is about asteroids and asteroids with moons. So this is an asteroid with a moon. So they tell you about Ida and Dactyl, but they're just saying some other asteroid and moon now. So the moon is 2 kilometers wide here, and the moon is 120 kilometers from the asteroid, center to center. The asteroid is 55 kilometers long, and the moon's orbit is circular. So the first thing is you have to realize here that, hi Sydney, that's the cat crawling up to be with me, but hopefully she won't get on my lap this time. So the first thing you have to realize is the size of the asteroid and the size of its moon are actually irrelevant. What's important is, and now she's on the couch behind me licking my hair for some reason. This is gross, but I'm going to stay here and let her do it. What's important is the distance from the asteroid to the moon and the period of this orbit. Right, because when we do like the moon and the Earth's orbit and all that, we don't care about the size of the moon or the size of the Earth. We just care about the distance between them. So the period, we get the period of revolution here. Let's see, I'll just say t for period of revolution, and we get the distance from the asteroid to its moon. So what we do here is we say, we want to find the mass of the asteroid, right? So I think we're assuming that this asteroid is massively bigger, or is much, much, much bigger than its moon. So, if you were, you might know that technically the period of a two-body system is proportional to, you have to deal with the total mass of the system. But in a lot of these cases where the mass of one object is much bigger than the mass of the other, you can just ignore the tiny one and just use the big one as total mass. So we're supposed to find the primary asteroid's mass. So first thing we do, of course, is as we always do with these circular motion problems, every circular motion problem you can pretty much bank on having to find the acceleration or the magnitude of the acceleration. So what we do here is we say acceleration equals v squared over r, and we also know by now, because this has been done 5 million times, that v squared over r is actually 4 pi squared r, and I should make this capital R since I used capital R there. Okay, so 4 pi squared capital R, and I guess, technically that, over t squared. Okay, so that gives us our acceleration of the asteroid. Now, what's causing the asteroid to accelerate? Force. Obviously, it has to be a force causing the asteroid to accelerate, and the force in question is, needless to say, the gravitational force from the primary asteroid. Sorry, I should say that they refer to this as the moon and this is the asteroid, even though the asteroid's moon is really pretty much another asteroid. But anyway, okay, so the force we can find, well, first of all, we can find, the force here by saying F equals ma, and then so we multiply this by m, and I'll put the m at the end here to make it cleaner, but you get the idea. So the gravitational force, the force we calculate by applying the gravity equation, the magnitude of that is capital G times mass of the asteroid, mass of the moon, over r squared. Okay, so we set these two equal, right? So 4 pi squared r over t squared. And then what this is, times m, sorry. And then what this is going to do, cancel. What this is going to do then is reduce into Kepler's equation, or Kepler's third law, second. I don't even remember. I can never remember Kepler's third law versus second law. I think this is Kepler's third law. This is going to reduce into t squared over r squared equals, let's see, so then t squared comes up here over r squared, r cubed actually, because we have this r here. I've done this 5 million times. I should know it better than this. Equals 4 pi squared over gm. So if we want to find m by itself, I guess what we should do, because that's what we're trying to find, the mass of the big asteroid, is going to be, oh, come on, Smith, figure this out. 4 pi squared r cubed over gt squared. That's m. So let's plug that into our little power toy calculator. 4 times pi squared times And mass of the asteroid, oh, we don't have the mass of the asteroid. We have, we have r cubed, and that's over gt squared. Okay, so r is the distance from the asteroid to the asteroid, or asteroid to moon, sorry, 120 kilometers. Okay, 4 pi squared, and so it's 120 kilometers, 120 kilometers times 1,000. So I'm just going to plug in 3 more zeros there to make it meters. Remember, we do everything in meters, kilograms, newtons, and seconds, and then it comes out. Okay, divided by, and again, let's look at our thing, g times t squared. Okay, so divided by, g is 6.67 times 10 to the minus 11th, and that is multiplied by t squared, which is, t is 28 hours, they said, and so we multiply by that by 60 to get minutes, and by 60 again to get seconds, and we square that, and then close the parentheses and everything, and this should give us the mass of the asteroid in kilograms. And my God, it's a lot. So let's see. Oh, I wish there was some way to. I don't even know. No, this is just. Oh, that doesn't help. Oh well. Anyway, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think 16, 17. So I'm just going to try answer divided by 1e17. Okay, great. So the mass is apparently going to be almost exactly 1 times 10 to the 17th kilograms. So I'm going to say 1.01 times 10 to the 17th kilograms. Okay, so 1.01 e17 kilograms should be the mass of the asteroid. Let's see if I get that right. No, I got it wrong. So great. Now what did I do wrong? Let's see. 4 pi squared times 120 cubed divided by. Huh. Well, now I don't even know what I did wrong. 1.01 e17. And that should be the mass, right? So what have I done wrong? Oh, 25 hours, not 28. I probably got 28 in some other version. Okay, well, that explains it. Okay, that's pretty duh. So there, this is going to be, it's the same length. It's going to be the same exponent. So it's really just 1.26. Okay. And now if I go down, and yeah, there we go. Okay, great. So now the volume is 14,100 kilometers cubed. What's the density? Well, now this, I mean, I feel like I shouldn't even need to write this down, but so the relationship between volume, density, and mass is that density is mass divided by volume, right? And this seems kind of duh, but let's remember, well, actually we don't even need to go any further than that, but let's remember here that they're giving the volume not in meters cubed, but in kilometers cubed. And what's the conversion between kilometers cubed and meters cubed? And I think some of you guys got tripped up on this, but if you have a cube that is a kilometer on each side, so it's a kilometer, kilometer, kilometer. How many cubic meters are in there? So it's a meter. Really, I draw a little cubey thing there. So that's meter, meter, meter. How many little meters cubed are in there? And there's 1,000 meters. 1,000 little boxes can fit up. 1,000 boxes fit on a side, and then 1,000 boxes fit on this side. So it's actually 1,000 times 1,000 times 1,000. So the conversion rate is not 10 to the third, it's 10 to the third times 10 to the third times 10 to the third. So it's 10 to the ninth. This reminds me of an old Bugs Bunny cartoon where Bugs Bunny and Daffy Duck were in a race to win something called $1,000,000 and on a game show. And so they went through the whole race, and finally Daffy won, and he won the $1,000,000. But it turned out the announcer had kind of a lisp or something, and the $1,000,000 was actually something called a million box, which was a big box called the million box. When you opened it up, there were 1,000,000 little boxes inside. And I remember looking at that and thinking there were only 100. I mean, well, there were less than 100 when they drew it, but you could see there were clearly way less than 1,000,000 on one side. And I was sort of thinking that through in my head as a kid. And finally, my dad explained, well, you have to multiply 3 times. And so, yeah. But then the joke at the end was that Daffy Duck realized he didn't want 1,000,000 little boxes. He thought it was $1,000,000, not $1,000,000 or 1,000,000 boxes. So he he said he was going to give the boxes to, Bugs Bunny. And so Bugs said, well, thank you, Daffy. And the announcer said, well, that was very generous of you because each of the little boxes contains a dollar bill. Okay, so anyway, this is our mass here. We already have this. So I'm just going to take all this and divide this by, or actually just to make it clearer, I'm going to take answer. And now to make it clearer, I've wasted a bunch of your time. But anyway, divided by the volume they gave us. So 14,100 cubic kilometers. But I'm going to multiply that times 10 to the 9th so that I get it into cubic meters. And this should give me the answer in cubic meters, which is 8955. So 8955. It might be, yeah, I'm rounding it correctly. Doesn't really matter, but and so that should give me that should be the density. And now the web is being slow. A good rule of thumb to remember, something that's handy to remember, is the original definition of the kilogram was that it was the mass of of a cubic decimeter of water, which is a strange unit to use, but oh, fantastic. I think you're just going to take my word for it that I was right, because I don't know what else to do. Maybe my internet's down or something. And now the cat's crawling on my chest. But what's worth remembering is that this is the density we got here. The density of a cubic meter of water is 1,000 kilograms. That comes from the original definition of kilogram. So they defined meter first and then defined everything else in the metric system in terms of meters. So the density of a kilogram is, the mass of a kilogram is, well, basically it's 1,000 kilograms in a cubic meter. So that's the density of water. So you figure this rock, it can be, this is denser than water, but it's not like 100 times as dense as water or 1,000 times as dense as water. And that makes sense, right? You wouldn't expect a rock to be 1,000 times as dense as water or something like that. So if you're ever finding a density of something and it's some ordinary material, it should be on the order of, thousands of kilograms per cubic meter. If you get like, 1,000,000 kilograms per cubic meter or more than that, you better be dealing with some kind of really exotic material like something at the core of a planet that's super, super dense or something like that. Anyway, that's all I'm going to yammer on about that. That's problem 5.